questions about anything? Last time or anything? Well, emphasize again that I'm doing Darboux's version of the Riemann integral because I think it's the more preferred way of doing it. Many famous textbooks in analysis do it that way. I kind of don't like the terminology of the book. That they call it the Darboux integral. The fact is the Darboux integral is the same as the Riemann integral. It's just an easier way of thinking about the whole thing. So we'll remark the Darboux integral is the Riemann integral. They mean exactly the same thing. Were there any questions about anything? I thought I should say a couple more words about some of the stuff I did at the end of the last hour. So the way we're defining things is we have a partition. P, and of course a partition means we have a bunch of xn minus 1 things, and we define the little m sub n to be the inf of f on my in. So this thing right here is in. And we define capital M sub n to be the sup. So when the f is continuous, you can think of the inf and the sup as being the min and the max. Okay, and let's see, I defined the lower sum of p, and if it applied to a function f, is equal to the sum as n goes from 1 to n of this inf times the length of the interval, which is xn minus xn minus 1. And of course, it's automatically true that that's less than or equal to the sum with the sups in the same place. And that's what we're calling the upper sum. Okay, and in order for these things to make sense, we need f to be bounded. So a note, f must be bounded for this to make sense. The Riemann integral can't be defined for something that's unbounded. The Lebesgue integral has no such issue. So we'll always assume that f is a bounded function when we're talking about these things. Okay, so one of the things I showed last time, and I did it by a picture. The fact is that if you add a point to a partition, those things go up. So if you get p prime from p by adding a single point, then those the L's can only go up, and the U's can only go down. Let's add the point x prime. Then the fact is L of Pf would be less than or equal to L of P prime of F. And of course that's always, this one's always a given. This is less than or equal to U of P prime of F. And by adding a P prime, that can only make the U's go down. So the L's can go up and the U's can go down. And if you do this multiple times, then you can see that the same is true about adding finitely many points. So repeat. See, the same is true adding finitely many points. Some number of points. M points. Okay, so I'll show that, I'll show the right-hand side. So I'm going to be careful about it now. Last time I just drew a picture and wasn't terribly careful, but it's important to believe these things. So let's do the proof that U of P prime F can only go down. Okay, so I've got my usual interval, xn minus 1, xn, and I'm adding an x prime in here. Then those sums for the U would be exactly the same except for the one in the middle. And the one in the middle would be, let's see, the prime one would be dot, 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 plus, let's take the min, let's call it m prime. M prime 1 times xn, x prime minus xn minus 1 I'll call it plus m2 prime. These are maxes, sorry. I'll call it m1 prime plus m2 prime times xn minus xn minus x prime plus blah, blah, blah. So that's the prime one. And this m1 is less than or equal to mn. And this m2 is less than or equal to mn. So when you add those up, they would be less than or equal to mn times x prime minus xn minus 1 plus mn times xn minus x prime. And now you can combine those. Let's see, I'll have the dot, dot, dots plus dot, dot, dot. And when you combine those things, you get mn times xn minus 1. And so check. That thing is equal to U of P comma F. And so it can only go down. And that would be the gory proof of it that I did with a picture. And similarly, the L's can only go up. So the U's can only go down. Similarly, the L's can only go up. Okay, so now when we use this fact, if I want to compare let's call it P1 and P2, the trick then is to take their union. So here's the trick. Let P be equal to the union of the two. So I get P by tossing in the points in P2 that are not in P1. So let P gotten by tossing in points in P2 that are not in P1. One at a time, and applying the previous stuff. And when you do that, you get, let's see, you'd get the L of P1, F. That would be less than or equal to the union thing. So that would be less than or equal to L of P, F. And of course, that's less than or equal to U, P, F. And the union being bigger, more refined, and that can only go down, that would be less than or equal to the union, the upper sum of P2, comma F. Notice I have P1 on the left and P2 on the right. But that shows you that all the lower sums are less than or equal to any of the upper sums. And that's a major theoretical moment because it means the L's are bounded above, the U's are bounded below. So we see all L's less than or equal to all U's. And so L's are bounded above. That's an important moment because now we know the soup of the L's exist. And the U's are bounded below. And so we're justified in defining the lower integral as being the soup of all those things over all partitions. And those would automatically be less than or equal to the inf of all the things to the right, because those are all upper bounds. Over P. And that's what I'm calling the upper integral. And remember when I was drawing pictures, the lower things are the area under the curve, and the upper things are the area over the curve for a given partition. It's too big. The L's too small, the U's too big, if we're looking for the area under the curve. And so something is Riemann integrable if those two things are equal. And we can squeeze the area in between them. And there's only one possible choice for the area. A bounded function f is Riemann integrable if L of f is equal to u of f. The fact that it's bounded means those things are defined. And let's see, so now it's a good time to start thinking about examples. Let's do the classic example of the rotten function, the function h of x, which is, say, 1 for irrational, and 0 for x rational, is not integrable, is not Riemann, is not Riemann integrable. Because, you know, that all the capital M's would all be +1, and the little m's would all be 0. And when you add up let's see, if I was doing this on integral, if I was doing this on interval AB, all the lower sums would be 0, this h. And all the upper sums, those mn's would be 1, and when I add them up, that would be a sum, as n goes from 1 to n, of xn minus xn minus 1. You get pairwise cancellation, the telescoping, and that would add up to b minus a. And so those two things, the soup of the L's would be 0, the in for the U's would be b minus a, and they're not equal. So no deal. So there's something that's not Riemann integrable. It turns out that all your favorite functions are. Here's a mind-blowing thing. I'm not going to show it to you, but the book shows it to you. That Tomei function, even though it's pretty wild and crazy and discontinuous in a lot of places, function is. That's mind-blowing. And the book shows you. I'm not going to do it because I want to get done with more things. Plus it's technical. Not terribly technical. It's a paragraph. But it's mind-blowing. Remember the Tomei function, t of x equals 1 over n if x is m over n is rational. So, of course, I mean it's rational. And m and n have no common factors. That makes them uniquely defined. And it's 0 if x is irrational. It had a really weird graph. I drew it back when we looked at it. It has the feature that it is continuous at every irrational. It's continuous at all the irrational points. Of course, there's a lot of those. It's continuous at the irrational point, but not continuous at the rational ones. Okay, so That's the rational numbers are countable. And remember, that's a set of measure 0. So it turns out that t is continuous. The word is almost everywhere. Everywhere but a set of measure 0. And that turns out to be exactly what you need for the Riemann integral to exist. That's a more advanced fact we are not going to get into. I'll write it down as a statement at some point, just so you can talk about it in the future. And a mind-blowing thing, hard to believe when you look at the graph, but the integral from 0 to 1 of the Thomé function is at 0. Of course, you believe that when I talk about Lebesgue integral, because it's 0 on all the irrational numbers, which is a set of full measure. So, so the rational numbers are so sparse from that point of view that they don't affect the integral. Okay, that's fascinating. Here's something that you might call the Cauchy criterion. For integrals, for Riemann integral. If you can find a partition for which if there is a partition, let's see, if for every epsilon bigger than 0, there is a partition P such that, let's see, U is always bigger than L, so U, P, F minus lower sum is less than epsilon. So we know that this thing is always greater or equal to 0. The news is that if it's for every epsilon, we can find a partition such that that's the case, then the lower sum has to be equal to the upper sum. I should say, what am I calling these things? Lower integral, upper integral. What does the book say? The lower integral. I don't know why I suddenly. Then those are equal, and so F is Riemann integrable. I guess I should have mentioned that we're assuming that F is bounded. Okay, and so using this is an important thing. Let's see, the proof is nothing. All those things, all the L's are less than or equal to all the U's. And so if you find one that's getting on the right that's really close to one on the left, the sups and imps have to be the same. Especially if I'll say the proof is just follows from the facts we have above. I won't dwell on it. It's an inf sup fact. So I'll call it easy. Just so I don't kill too much time in class today. Do I need to think about it? Honestly, think about it. Anybody not believe it? Well, this little fact is going to allow us to see very simply that a consequence is monotone functions are Riemann integrable. Okay, let's see why. I guess I drew pictures like this last time. Monotone functions can have jumps, remember. In fact, they can have countably many jumps. I'll do the increasing case. Maybe I'll do the case with no jumps. When you do the whole partition business, so I'd have a B here, an A here. You'll see in a minute why I'm going to make my partition be delta x's of all the same length. So let's let delta x be equal to b minus a over n. Then I get tick marks, spaced equidistance. And when I do the lower sums, see, I liked the lower sums are below the thing, and the upper sums are above. And notice that the soup is always happens at the right endpoint. What am I doing? Is that right? Yeah. So the orange ones are the m's and the green ones are the little m's. So when I add those up, so let's see, if I have an interval like this, here's x sub n minus 1, x sub n. We see that the m sub n is equal to f at xn. And the little m sub n is the left endpoint. Okay. And so when I add up an upper sum, let's let epsilon be bigger than 0. When I add up an upper sum, I would have an upper sum of this partition with equal delta x's minus the lower sum. That would be a sum as n goes from 1 to capital N. The upper numbers are f of xn. Let's see, I'll write mn minus mn times the delta x. And these things we've seen are f of xn minus f of xn minus 1. And that's equal to, here's the important thing. This is why I did the delta x business. I can factor out the delta x. If I didn't make the equal delta x's, I couldn't do this last step. So that's why it's important. And then and now this is a telescoping sequence. And so this telescoping sequence spits out f at the right endpoint minus f at the left endpoint. And so here I get delta x is b minus a over n. And here we get f of b minus f of a. And now the good old Archimedes principle says I can choose an n to make that thing less than, so let's see, I want this to be less than epsilon. And you see I should take n bigger than b minus a times f of b minus f of a over epsilon. Check. And exactly the same thing can be used to show that here's a biggie. Continuous functions are Riemann integrable. Let's see, what does the book say? I think they use this notation to say that something's Riemann integrable on AB. Riemann integrable on AB. That's a biggie. And it turns out to be a very simple thing now that we've got the machinery in place. So that the reason is because f continuous on a closed interval implies f is uniformly continuous. That's why we worked so hard to see that. You didn't see why that was going to be important at that moment, but this is exactly why it's important. We need a uniform continuity. Okay, and that means I can do the same business with the delta x that I did above. And let's see, do the same routine above. Let's take delta x equals b minus a over n. Then when we look at the sup and the infs, we'd have a xn minus 1, an xn, and then we'd have a sup and an inf. The sup, our f might look like that. You ask yourself, how could the inf be close to the sup? Really close. So let's let epsilon be bigger than 0. This is a typical thing to do. This orange one is the capital M, and the green one is the little n. Then we know by uniform continuity that there is a delta such that I'll use I should have used, I'll say y1 minus y2 less than delta implies the f of those things are less than epsilon. Well, where's the y1 and the y2? We know that a continuous function on a closed interval assumes its max and its min. So this would be our y1 maybe, and this would be our y2. And so if the delta, if I make that this delta x less than delta, then I'll have that the max and the mins. So the important thing here is max and mins are assumed. We know that. On the closed interval. It could be a left endpoint or a right endpoint. That'd be okay. So the aha here is we want b minus a over n to be less than delta. And then what we get, then UF for that partition minus the lower sum. I'm probably not going to get epsilon here, but I'm going to get something at least. Would be less than the sum of the upper sum minus the lower sum times delta x and these would all be less than epsilon. Let's see, the mn minus the would be equal to f of y2 minus f of y1. And of course that's a positive thing. So that's going to be less than epsilon. So the way I've drawn it, that's going to be got to be positive because it's a max minus a min. Greater or equal to 0. And this is less than epsilon. So I'm going to get that whole thing is less than the sum, less than or equal to, this is not less than, this is equal. Less than or equal to epsilon, the sum times the sum of the delta x. Oh, crud. I'm using n in two meanings here. I'm using it as a dummy variable. I'm using it, here's what I should have done. Okay, do the same routine, except this time I'm going to use a capital N here. I might have made the same mistake previously and not even thought about it. And so, of course, this thing here is, you can factor out the epsilon, and the sum of the delta x's are b minus a, because it's n times b minus a over n. Oh, hallelujah, it's actually, I actually get an epsilon. If I got the wrong thing here, oh no, I don't get epsilon. Do I? Oh, I do. No, I get b minus a times epsilon. So this is equal to epsilon times b minus a. That means I picked kind of the wrong epsilon. So that's pretty good. Go back and replace epsilon by epsilon prime equals, what should I have had? I should have had my epsilon divided by b minus a. and repeat. You get an epsilon at the end here. And after you do that a million times, you realize you don't have to mess around with that. Epsilon times something is just as good as epsilon. So that's all there is to that. That's important fact. Let's see. Oh, let's see. There's a whole bunch of things that are kind of tedious to watch, but important to read the book. For the proofs of the easy facts. Let's see, there's a whole bunch of them. For example, if I have A, B, and C, then the integral from A to C is equal to the integral from A to B plus the integral from B to C. Stuff like that. You believe it because you know it represents areas and areas add, but to demonstrate it using the definitions is somewhat tedious. And let's see, other things like the integral from A to B of k, a constant, times f of x dx. You can pull out the constant from the integral. That's easy to believe and even easier to prove. And of course, the book uses space to do it. And then things like if two functions are Riemann integral, then their sum is Riemann integrable, and etc. The integral is the sum of the integrals. All that kind of stuff. Well, I want to do something exciting today. And I thought I should demonstrate the fundamental theorem of calculus in 3 minutes. But now I'm having second thoughts. Might be getting kind of tired. Oh, let's see. There's another important fact. Integral if f is less than or equal to g for all x, then of course the integrals are less than it. You can just see that by looking at the soups and the inf and saying, aha, yes, every single thing. That's easy. And so in particular, if m is like a minimum, and m is a maximum on an AB, m times b minus a is less than or equal to the integral from a to b of f dx is less than or equal to m times b minus a. That's an easy one to get. And next time I'm going to use these basic facts to demonstrate the fundamental theorem of calculus, which is an exciting moment in history. It's why Newton and Leibniz, they needed it really bad to study velocities, and they both came up with the same idea at the same time. Kind of a miracle in history that happened that way. And now with the basic facts of integrals, it's a very simple, easy thing to do. And that's why it's one of the few things that we actually demonstrate in freshman calculus, because it's so straightforward. And I'll do it, I think I'll save it for next time. To finish off today, I'll mention these famous fact. A function f on AB is Riemann integrable if and only if one, f needs to be bounded, f is bounded, and it needs to be continuous almost everywhere. So there's a fancy word, almost everywhere. That's the famous fact. And the proof takes some time. And if you're using calculus to do engineering and science, I don't think you ever need this fact. But it's a nice fact to know because it's sort of a philosophical fact. It's how good is the Riemann integral? And this is what people were convinced it's not good enough because there's some weird functions out there that certainly don't, like the irrational rational thing, 1 and zeros. Looks like it ought to have an integral, but it doesn't. Okay, so the Thomé function is such a function. So remark, the Thomé function is. And it's continuous on a set of, so here's what almost everywhere means. Means on the whole whole AB minus perhaps a set of measure 0. Minus perhaps a set of measure 0. And measure 0 means I can cover it by a bunch of intervals whose lengths add up to something arbitrarily small. So measure 0 means I can cover it by arbitrarily small sums of intervals. Means given epsilon bigger than 0, there are intervals, countably many intervals, oops, I'm going to take open intervals, A and Bn, such that my set, so S is a set of measure 0, means that there's countably many intervals. S is contained